Welcome to Neural Networks and Deep Learning Introduction, part of the Fundamentals of Machine Learning course geared toward training AI practitioners. In this lesson, we'll uncover how neural networks function, why they're inspired by the human brain, and how they form the backbone of deep learning. We'll explain their layered structure and how they excel at tasks like image and speech recognition. Consider this your first step into a world where depth refers to more than just complex code. It's the key to solving today's most challenging data problems. Neural networks are computational models that loosely mimic how the brain's neurons communicate. Each artificial neuron receives inputs, processes them, and sends signals onward. As these nodes link across layers, the network learns intricate relationships, transforming raw data step by step into meaningful patterns. Think of it like adjusting dials on a mixer. Each dial fine-tunes how signals pass through the system. Over time, this tuning process yields a powerful mechanism for recognizing patterns or making predictions. Imagine a child learning to distinguish dogs from cats. Each time they see an animal, neurons in the brain form or strengthen connections. Over time, the child identifies key features: fur length, ear shape, or tail movement. Neural networks replicate this process, but in silicon, mathematical operations approximate how neurons fire. After seeing enough labeled dog or cat examples, the network's synapses, weights, adjust to correctly classify new images. This brain-to-machine analogy illustrates how neural networks learn and improve with examples. A typical neural network comprises an input layer, one or more hidden layers, and an output layer. The input layer collects raw data, like pixels from an image, while the output layer generates final predictions, e.g., cat or dog. Hidden layers in between transform those inputs step by step, often uncovering edges, textures, or other crucial features. By stacking multiple layers, networks create a deep model capable of unraveling complex patterns beyond the reach of shallow architectures. This layered design is the heart of deep learning. Neurons don't merely pass signals. They apply an activation function to decide if and how strongly to fire. Functions like sigmoid, TANH, or ReLU introduce nonlinearity, giving networks the power to model complex relationships. For example, ReLU outputs 0 for negative inputs and a linear value for positives, helping networks converge faster during training. The choice of activation function impacts both learning speed and capacity. Without these nonlinearities, a neural network would essentially be a linear model, limiting its potential. Data flows forward through a network during the forward pass, generating a prediction. The network then compares this prediction to the actual label, calculating an error. Next is backpropagation, or the backward pass, which adjusts each connection's weight based on its contribution to the error. This iterative process is much like a coach reviewing each play, pinpointing errors, and refining strategy. Over many training epochs, the network converges on weights that minimize overall loss and maximize accuracy. Picture a smartphone app that transcribes speech into text. Early versions might struggle with accents or background noise, but each time a user corrects a misheard word, that correction is new training data. Behind the scenes, the neural network updates its weights, improving recognition over time. This feedback loop exemplifies how networks learn continuously from real-world usage, getting better with every correction. Eventually, the app handles diverse accents and tricky phrases far more accurately than before. Neural networks, especially convolutional neural networks, CNNs, excel at image recognition. Companies like Google rely on these architectures for image search and auto-tagging. Convolution filters scan pixel grids for features like edges, curves, and textures, while deeper layers combine them into complex shapes or objects. Eventually, the network labels images with near-human accuracy. This approach powers everything from facial recognition in photo apps to advanced image-based diagnostics in healthcare. The impact of CNNs on modern image analysis is both transformative and far-reaching. Visualizing a neural network can reveal how it learns over time. You might see circles for neurons, with connecting lines thickening to represent stronger weights. Meanwhile, training charts can show how accuracy increases or loss decreases across epochs. At first, weights might appear random and error rates high, but as each epoch passes, the network refines itself, steadily converging on a solution. Such diagrams or charts help us grasp the iterative nature of learning, turning random initial states into purposeful models. Neural networks often demand extensive labeled data and significant computing power. Training an image classifier might require tens of thousands of images, like the massive ImageNet dataset. The more diverse and high quality the data, the better the network generalizes. Meanwhile, specialized hardware, GPUs or TPUs, can drastically cut training time by handling parallel calculations. Balancing data quantity, data quality, and compute resources is crucial. Too little data or insufficient hardware can hamper performance, while abundant labeled data plus powerful machines can unlock breakthroughs. If you're eager to practice, platforms like Kaggle offer a range of image, speech, and tabular datasets suitable for neural network projects. Competitions challenge you to build better classifiers, whether diagnosing medical scans or identifying plant species. You'll find example notebooks, active forums, and ranking boards. Observing top submissions reveals how seasoned practitioners engineer their networks. Beyond Kaggle, libraries like TensorFlow or PyTorch provide powerful APIs to create custom architectures. Diving into these resources accelerates your path from theory to hands-on implementation. Why did deep learning suddenly surge? A trifecta of abundant labeled data, powerful GPUs, and refined algorithms propelled neural networks to new heights. As the internet amassed billions of images, videos, and text snippets, data-hungry networks finally had enough examples to learn from. GPUs made fast, large-scale matrix operations feasible. Researchers improved architectures, like deeper CNNs or novel activation functions, leading to breakthroughs in speech and translation. Tech giants and research labs poured resources into this domain, fueling further growth in a rapidly advancing field. Consider self-driving cars navigating city streets. Sensors collect streams of images and distance data, which feed into a neural network that discerns lane lines, pedestrians, or other vehicles. Each detection influences split-second decisions, braking, steering, or accelerating. Trained on millions of driving scenarios, these networks learn how to handle complex, real-world conditions. Though still evolving, autonomous vehicles show how deep learning merges perception, pattern recognition, and decision-making in real time, shaping a future of safer, more efficient roads. Throughout this lesson, you learn that neural networks mimic the brain's neuron connections, using layers of weighted nodes to process and transform data. We covered their architecture, activation functions, the forward-backward pass, and the importance of large data sets plus specialized hardware. You also saw examples like speech recognition, image classification, and self-driving cars, all powered by deep models. By understanding how these networks learn and adapt, you gain the key to solving highly complex tasks once thought beyond machine reach. Neural networks shape some of today's most transformative technologies. From voice assistants understanding your words to self-driving systems navigating streets and medical tools diagnosing diseases. By mastering the core concepts of layered neurons, weight updates, and big data training, you stand poised to create powerful AI applications. Keep exploring frameworks like TensorFlow and PyTorch and practice with open-source datasets. Armed with this foundation, you'll delve deeper into advanced architectures and unleash your creativity in the next lessons. Congratulations on reaching this milestone.